This is a small experiment to show the strength of a magnetic field from an electromagnet hitting a regular permanent magnet. I have two types here. I have a neodymium magnet, very strong rare earth magnet, and here I have just a ceramic magnet, very weak magnet. And I've got a small scale here to measure the mass of each of them. So what I'll do is I'll start with the small one, and we'll take a reading. You can see the rare earth magnet on there. We'll take a reading, and then this is in grams, 30 grams max. So we've got 15 grams. So put that down, and then we'll take a strong magnet, and it, as you can see, it bottoms out the scale. It's more than 30 grams. I have another scale, but just we can see that it is more than 30 grams for sure. So it's more than double the weight of the previous magnet. Alright, so now we're going to do the experiment. And what the experiment entails is I have a coil here, just an air coil. As you can see, there's no core inside there. It's just air. And here I have a capacitor. And here I have a battery, 12-volt car battery. What I'm going to do is I'm going to charge up the battery into the capacitor, then disconnect it, and I'm using just the charge off the capacitor, which is 10,000 microfarads, to discharge that into the coil. And I'm going to place this magnet in front, and I've got a scale here, a ruler, measuring tape, whatever you want to call it, and we'll measure the distance of how far each pulses the magnet away, and see if there's a difference between the regular ceramic that I have here and the rare earth magnet. So here's our voltage. As you can see, it's reading 0.5 volt on the capacitor. So I've just got these cables here hooked up, and what I'll do is I'll charge up the capacitor. As I touch this on here, you'll watch the battery voltage go up. See if we can get this all in. There. Okay, so we can see I've got 12.57 volts, and it goes down slowly. Now what I'll do is I'll touch this on here, that'll discharge the capacitor, and we'll watch this go. Okay, now we can get a reading. It's about 11 centimeters. We'll do it again. We'll charge up the capacitor from the battery, disconnect the battery, hit the cap. Okay, well, this time we got a little more. Depending on the resistance and how it flies, we got 16 centimeters. We'll do another one. We'll charge it up again. 12.57 volts. We'll connect this again, and we're getting about 15 centimeters. So just do it one more time. See, it's about 15 centimeters is about the distance it normally goes. You do an average or so. So we'll do it one more time here. Charge up the capacitor. Put this on here. And we got about 13 centimeters. And we can see the capacitor is discharged. Okay, now we'll use the rare earth magnet to do the same experiment. Okay, so here's the rare earth magnet. I will place it in front of the coil, charge up the capacitor, now discharge this. Whoa! Okay, it stuck to there, but it certainly went a lot further. We'll do that again. Discharge the cap. Okay, we're getting 27 centimeters, 26 centimeters approximately. Do it again, one more time. Place it back here. As you can see, the capacitor is discharged almost. Okay, we'll charge it up again. 12 volts. One more time. Whoa. Okay, that time it went 54 centimeters. So quite far. Do it again just to get some averages here. And you can see 0.4 volts in the capacitor. Charged up to 12.3, and we'll hit it again. We're getting 56 centimeters, and nothing, 0.1 volts in the cap. Charge it up. There we go. And we'll zoom out a bit so we can see this thing fully go here. Okay, get caught around there, but we're getting like 45 centimeters or so. Now I'm going to do something else. What I've got here is two regular ceramic magnets, so I'll double the mass on this. So this is about 30 grams. And what I'll do is I'll place these here, see if it gives us anything more. Now, double the field strength, but I double the mass. Okay? So again, we'll charge up the cap and place this on here. And what? 13 centimeters. So basically we're getting the same as before with one. Double the mass, and we get double the field strength, but we also get the same distance. So it's showing that the field strength and the mass and the repulsion fields are all linear in proportion. Okay, so we'll discharge this one more time. Yeah, we're getting 15 centimeters. Okay, we'll do the rare earth magnet one more time. Cap's charged up, 12.36, and here we go. Way down here again. So it's really cruising. So we're double the mass, but remember the field strength of these rare earth magnets is about 4 to 5 times that of these ceramic ones. And we can see the cap's fully discharged. And I'll just do this one more time to show the cap is, make sure the cap is fully discharged on the ceramic one here. So the cap's discharged, charge it up. Now, placing this, all I'm doing is placing this on here, and that's connected to the coil and the cap. That green wire goes to the cap, but it's not connected to the battery at the moment. So just charging the cap, 12.25 volts. Here we go. And we can see nothing in the cap. And let it fully discharge, and we're only getting about 17 centimeters. So anyway, that's just a proof of theory and concept that no matter if you start off with the same amount of energy in a capacitor, we know that that's 10,000 microfarads at 12.5 volts, we'll call it. We can calculate how many joules, and we know the distance that it's pushing these magnets, and we can see that a stronger magnet of more mass with a higher field strength will push farther away. So I'm not putting any extra energy into this system with electrical joules, electrical energy in joules from the capacitor or battery, yet I'm getting more power, more distance out from just using a stronger permanent magnet. And this can be taken advantage of in motors and many other applications that require power. Is it free energy? Well, I mean, the energy is stored somewhere. It's stored in the magnet, and it's pushing back against this field, and the stronger the energy is, it's proportionally non-linear. I would say, well, proportionally linear to the field strength of the permanent magnet being used, but not linear to the, or not proportional to the strength of the coiled in the field of the magnet, how much energy is put in there. So this has great applications for many things. Let your imagination go with you on this, that's for sure. And that's all for now. One more shot of these rare earth magnets. You can see how powerful they are. Ow! Anyway, okay, that's enough.